what we had. So group 1, and I know I get it. Some of you guys don't want to speak out loud, but if one person can unmute and just share, what did you guys get for example 1 out loud to the group? And then some of you guys type it out as well if you were part of that group. Let me see if I can actually hear you guys. So go ahead, group 1. What did you guys learn?
We got infinity for the 1 over x dx.
Okay, perfect. Did you guys also happen to do, and I know I didn't happen to share my screen, and I thought I did. Did you guys happen to do the 1 to, did anyone do the 1 to infinity 1 over x to the 1/2?
Yeah, we did both.
Oh, okay, perfect. What did you get for that one?
We also got infinity as well.
Okay, and that it diverges. And right now, if the rest of you guys can record as we go through each group's findings, group 2, can someone unmute and let me know what you guys got?
We got 1.
Okay, they got it converges to 1. Perfect. And just as we're doing this, I know you guys watched a video on it, but the idea of this is that as it's approaching the x-axis for these, that you actually have, it's converging to an actual area. So the first 2 problems, the divergent, it's not, the tail end of the function isn't getting close to the x-axis fast enough so that the actual area converges to a value. So we get divergent so far, then converges to 1. And actually what I'm going to do is a little bit purposefully put 1 over 1 here. Group 3, can you share what you guys got?
So for 3, we got converges at 1/2.
Converges at 1/2. Perfect. Group 4.
1/3.
1/3. Group 5.
1/4.
1/4. And group 6.
1/5.
1/5. And if I had a group 7 with x to the 7th, what do you guys think the answer would be? Okay. All right, so there is definitely a pattern that emerges here. So what we call this eventually is something, and I'm going to throw this word in. I know it sounds scary at first to hear, but this is called a P series, okay? And the word series means that somehow this is going to come back to haunt us in the next chapter in a really big way. And I kind of start that discussion with you guys on Thursday's lesson. Thursday's lesson is kind of partially this chapter and a little bit of next chapter, with it, the focus of it just being introducing you guys to this idea. Okay, so a P series is named a P series because of the exponent at the bottom being P. Okay, so what we found was that 2 results emerge. And first I'm going to talk about what happened with group 1. Yes, so all of groups 2 through 6 converges, and then the top 2 diverges. So what we're going to say is for the top one that my answer is infinity or diverges when P was a certain value. Okay, and that was when P was between 0 and 1 inclusive of 1. It can't be equal to 0 because then it would no longer be a P series function. 1 over x to the 0 is just 1. So here's where I want you guys to make a conjecture for me. We know for sure, like Sophie just asked, groups 2 through 6 did converge. We can be even more specific in our description of what it converges to. Anyone in the chat or out loud? How do I come up with the value to which it converges or the area under the curve? How do I come up with a shortcut for finding that without necessarily having to integrate? Okay, one person typed it into the chat correctly. That is right. Okay, excellent, you guys. So if you notice the pattern, the value at the bottom here is 1 less than the exponent. So it corresponds with the group number as well. So if you guys look at the exponents, it's always 1 less than that. So the summary is that it will converge to, so I'll say converge to 1 over P minus 1, so long as P is greater than 1. Not equal to, but greater than 1. Okay, so when I look at a p-series problem, I'll automatically know, okay, that's convergent or that's divergent just based off of the pattern that I'm observing. Okay, so what we're gonna do is move on to just a review problem of a larger, more difficult question from the part A lesson that you guys did. So the part A lesson that you watched the video on, and I really sincerely hope you guys all watched that video prior to coming to class, because we jump into kind of a difficult example. So the video was on these examples that you guys see here. So if you didn't get a chance to watch it, again, make sure you guys go back, watch that part A video. So page 2 we've completed. If you guys can go to page 3, I'm going to talk about this top one, which to me, what makes this chapter difficult is the improper integral problems that then entail things like L'Hopital's rule. So we see an integral problem, we see a derivative within an integral, and a limit there. So all of that stuff combines to make these questions very complex, in my opinion. So I did title it Using L'Hopital's Rule with an Improper Integral, and I'm going to do one with you guys. Eventually, I'll have you guys do a classwork problem just so that you get a chance to talk about it. Okay, so this is going to be our example for today, along with a few other part B questions. So what I'm going to have you guys observe here is this is, again, part of the video lesson that you guys saw. You could have seen this on a homework assignment, although I think it's difficult in the sense that you have to remember all the stuff from first semester. So when I initially look at this problem, I noticed that 1 minus x and e to the negative x, this isn't going to be it's definitely not basic integration. It's definitely not u substitution, because if I let u be equal to anything within the integrand, its derivative is not going to help me get rid of anything and replace it with u. So if it's neither one of those, then I have to just continue to explore. And one suggestion I would have is to distribute the e to the negative x, right? So what we're going to do is rewrite this 1 to infinity, e to the negative x minus x e to the negative x dx. Now at this point, you guys will notice there's two terms, where the first term I can easily integrate basic integration. Can you guys type into the chat or out loud? What do you guys think? What technique did we learn that allowed us to integrate x e to the negative x? What type of integration is this? X e to the negative x. Very nice, you guys. Well, some of you are typing out, yeah, Voodoo or tabular, which is a shortcut for types of problems where you had algebraic and then exponential at the same time. Excellent. Okay, so here's every time you guys do an improper integral, and I know I'm not going to get compliance with all of you guys doing this every single time. So I'll say if it's for a multiple choice question, I know some of you guys are going to skip writing it as a limit. And that's okay. It ends up being the same thing, like plugging in infinity, so long as you have the idea that it's approaching infinity and infinity is not a number. Then on a free response, though, they're going to expect that you guys properly notate your steps along the way. So what that means is that there's two things going on. First, I'm going to rewrite this so that it's a limit problem. And secondly, on the side, what I'll do is I'll integrate without worrying about the limit and come up with the antiderivative, because this antiderivative is going to be more complex than our examples that we saw on the video. So first, recognizing that it's improper. So the video that you guys watched, it's easy to spot part A type of improper integrals, because what you have is the problem being infinity here. You're letting x approach infinity. And so since infinity is not a number, we're going to replace it with the variable b and make it a limit as the integral goes from 1 to b, and then separate this e to the negative x. And because I'm doing this as two separate integral questions, you can also separate this and say, okay, I'm going to minus the limit as b approaches infinity of 1 to infinity of x e to the negative x dx. Sorry, I forgot the dx on the first integral. So just take a moment there and look at what I did. I did not replace infinity there, so this should be b. So I basically rewrote my improper integral so that b was in place of infinity. Okay, and so this is the proper notation for what you're doing. And then what I'm going to do is switch colors over here. I understand that I'm going to have to integrate something that is more complex than I would like, and I might not want to write limit as b approaches infinity each time. So actually what I'm going to do is, don't like the red, so I'm going to switch to green here and integrate this. A couple of you guys mentioned voodoo, which is the correct thing, integration by parts. And with integration by parts, this is a refresher on it. ILATE was the acronym we used to let U be equal to either the algebraic portion of the integrand or the, in this case, exponential. So in this case, we see that x is algebraic, e to the negative x is exponential. And anytime we have something that's algebraic that precedes a trig function or exponential, we could use that shortcut tabular. So I'm going to do tabular on this. Okay, so on one side you guys have u, the other side you guys have dv. With tabular, you let u be equal to the algebraic, dv be equal to e to the negative x. Remember, tabular only works if you guys have something that is algebraic with trig or algebraic with exponential. Okay, the reason being that as you guys take the derivative of the left, you're going to get 1. Then the derivative of 1 is 0. So the successive derivatives get simplified enough to where it eventually becomes 0. And so you have no terms left. On the right-hand side, if you guys successively integrate that, you have e to the negative x is itself. But then remember, we have to undo the times by -1 by dividing by -1, which is essentially the same thing as timesing by -1. So in your head, just take the derivative of that. Does that match? When I take the derivative of this, does it match that? And yes, it does, right? E to the negative x, its derivative is e to the negative x times -1, which gets us that positive. So keep going, you guys, go a couple of iterations with this. If I do that process again, it becomes positive. And just for, I guess, so that it matches out when I do it. I think the last step was enough, but I'll just do one more step with the e to the negative x. And then from there, we had signs that went in between, alternating plus, minus, plus, minus. Okay, and then multiplication, where you guys would multiply x and the positive sign with the second term, which is v. Remember, it's uv. So keep going with that pattern. Okay, so I have my antiderivative. My antiderivative for this expression right here is going to be this term multiplied together, plus or minus this term, minus in this case, and then this is 0. So going back to my actual limit improper integral question, now I'm going to go ahead and do the antiderivative for each part. Okay, so this was a separate term, not part of the integration by parts. So we're going to integrate this. The antiderivative of e to the negative x is, we saw on the other side, negative e to the negative x. That's finding the antiderivative. Then I have to evaluate by plugging in b and plugging in 1. Okay, so that'll be the next step. Over on this side, we also found the antiderivative using tabular on the right. So now collecting all our terms, we have negative x e to the negative x. That's the first part of my tabular. Then I have minus x e to the negative x. Okay, and then at this point, I'm going to pause real quick. Does anyone have any questions on where I got certain things? And then again, put 1 and b here because we have to evaluate the FTC part of it. Any questions so far on what I did? Oh, yes, that is a good question because I made a mistake. So here it was x times negative. This one should be just negative e to the negative x. Thank you. So correction here, can you guys double check your notes that it just says minus e to the negative x? Okay, so that came from this one. Thank you. Okay, So as I plug in b and 1, and just to get you guys familiar with this step, you guys, if I had to name the number one mistake in this improper integral stuff is this step right here. I mean, aside from the fact that you guys have to remember all these other complex things like integration by parts within a problem, this step is crucial as you guys plug in. And if you have a negative exponent, please, please, please rewrite your negative exponents as positive exponents by bringing that expression down into the denominator. Please do that, because then it makes our evaluating of the limits much more straightforward and easy to do. So watch what I do. I'm going to keep the limit as is, but as I plug in b, I'm going to rewrite it as -1 over e to the b, or sorry, -1 e over e to the b, positive because you guys brought it down. And then when I plug in 1, I'm going to remember it's minus that expression. So it's going to be plus 1 over e to the 1. Okay, so bring down those negative exponents. Minus, limit as b goes to infinity. Do the same step here. Plugging in b for all your x's. Okay, here's the tricky part, and take your time as you guys do this. If it helps you guys, put parentheses here. This is the parentheses from plugging in the b, and then you have a minus the expression with 1 plugged in. Okay, if you guys can just double check that you understand where everything comes from for now. There's a lot of B's and E's going on here. Just making sure that it makes sense to you, how I wrote that it makes sense. Okay, and just walking you guys through it again. Recognizing something is improper is really important. Seeing the infinity in one of your limits of integration, rewriting it as a limit problem. Then the next step would be integrate. Ignore the whole limit part for that. At that point, just integrate, think of all the techniques you guys learned before. Then at this stage that we're on right now, this is when you guys start doing the limit part of it, right? So now each term, we're gonna let it go to infinity. So can you guys type into the chat, if you plug infinity in for b at this point, what would this first term be? And that'll make it simple for the other ones. Okay, you have a big bottom, which means that you have 1 over a million. Very good, it approaches 0. So if you guys like, you can also just like slash it through and understand that that limit is 0. Okay, you get a constant value for the next one. So for that one, I'm gonna rewrite it eventually, but I'll keep it the same color for now. Here's where, you know, the very beginning, it was titled Use L'Hopital's Rule with Improper Integral. In theory, you guys are using L'Hopital's rule when you get to this part, because when we plug infinity in, we have negative infinity over infinity, which is the indeterminate form. So I know that if I were to take derivatives of the top and of the bottom, that it's going to result in a constant at the top and e to the b still at the bottom, -1 over e to the b, which is going to give me what value? If I apply L'Hopital's rule to this, what would I get for this? If I apply L'Hopital's rule here, what would I get? Okay, and L'Hopital's rule is, yeah, just successive derivatives, right? I would get -1 on top, I would get e to the b on the bottom. Plugging in infinity, you guys would get a million at the bottom. So it's still going to result in you guys getting a 0 overall. Okay, does that make sense to you guys? If you apply L'Hopital's rule, if that was a single L'Hopital's rule question, the result of that would be 0. You initially have negative infinity over infinity, take successive derivatives of the top and the bottom, and it would still result in the limit being equal to 0. Okay, so same thing applies here. You guys plug in infinity, we get 0 for this term as well. So it's gonna lead us, to collecting all of our like or are combining like terms at this point. And yes, Sophie, sorry that your Wi-Fi's spotty, but yes, all lessons are always posted on the agenda after I've recorded it and like processed it. It's going to be on YouTube, and then I'll post it on the agenda as well. All right, you guys. So at that point, you guys have just constants left. So this is 1 over e. And then we have this minus sign that I'm going to carry down. And then distribute the negative sign. And you guys have 1 over e plus 1 over e, because I distributed this. Okay, so the result of this is, if you guys cancel out 1 over the 1 over e's, then it's negative 1 over e. And so all of that is to say that this initial integral does converge. Okay, so it converges specifically to negative 1 over e. And I'm going to have you guys add that because you guys, the series chapter is all about convergence and divergence. So just understanding that the integral test eventually is going to be this, is applying an integral, specifically improper integral, to determine if a series converges or diverges. For our sake, right now, we're going to envision this as the area actually approaches a specific value, and that value is negative 1 over e. Okay, so eventually I'm going to have you guys come back to this because I'm going to have you try it in your own breakout rooms. I'm going to move on to the next page with you. Does anyone need another moment before I move on? Any questions? Okay, you guys, so this next page is about improper integrals with infinite discontinuities. Okay, and infinite discontinuities were just a fancy way of saying vertical asymptotes. Okay, so infinite discontinuity, so I'll circle that. Those were vertical asymptotes. And we found vertical asymptotes, if you guys remember from the past, by setting the bottom of a fraction equal to 0. So vertical asymptotes occurred when the bottom, wherever the bottom was equal to 0, right? A fraction can't be equal to 0 at the bottom. Okay, what does that look like? So on the graph, let's say I'm looking at a function f of x on the integral from a to b. Okay, so I'm reading this. This is a to b of f of x. And I notice, and I'll sketch a graph for you guys on this side. Let's say that you guys had a vertical asymptote that went along x equals 1. Okay, and to the right of that, you guys had a function that was approaching that vertical asymptote. And so you guys kind of want to just flip this graph in your mind. And now the question is, if I was approaching this vertical asymptote, is this right part of the function approaching the vertical asymptote quickly enough such that the area exists? Okay, so the problem area now is this vertical asymptote as opposed to my x-axis as before. So here the question is this going to approach it quickly enough such that this area converges? And so your a value is going to be some finite value on this side. Your b value is going to be your vertical asymptote. Okay, and this occurs when you notice that it's approaching it from the left. Okay, so looking at my interval, and like, let me go ahead and underline this. This is my interval a to b. Notice that the interval is to the left of the vertical asymptote. Okay, so this is approaching from left. And if you guys remember back to when we were doing limits, approaching from the left meant that we had a little negative sign, which you guys will see, and let me zoom in on it. This little negative sign means that you're approaching it from the left. And this is what you guys want to visualize. The interval is to the left of the vertical asymptote. Okay, so from the right would mean that, let's go ahead and put from right on this bottom graph. And this time you guys have your vertical asymptote, let's say, still at the same spots, but this time your vertical asymptote occurs at A, it's on the left-hand side, and then B is on the right. You have a function, it's approaching A from the right-hand side, and we can remember this if we look at our interval, it's rightwards of the vertical asymptote. Okay, and the area that we're discussing is this area right here. And the area from above is this area right here. Okay, the tricky part of these questions is the part A type questions. It was really easy to spot it's improper. And I usually don't have kids having trouble with that because you see the infinity straight away in the limits of integration, right? In these ones, you guys are gonna see numbers there. So it's gonna look like a regular integral to you. So what we have to get better at is when we spot a fraction in the integrand, we have to address, okay, is this improper or not? It's only improper if there's a vertical asymptote within A to B, okay? And so the trickiest ones of all are, imagine if you guys had, and we'll just do a quick graph here, a quick graph over on for part 3. Imagine if you guys had a vertical asymptote here and you had the function approaching on both sides, like think of the 1 over x squared where it's on both sides, it's approaching the vertical asymptote. So we have to spot in kind of like an internal vertical asymptote on a range that could be A on this side and B on this side. So this is A, this is B, and the vertical asymptote occurs somewhere in between. So it's really easy to catch now that you know. But again, when we review for the AP test, I'll keep reminding you guys, every integral you should kind of consider if it has a fraction in it, we want to think, okay, is this going to be improper or not? The nice thing is that these don't come up too frequently because they just take a long time to do. And there's a shortcut for doing it. One other thing I'm going to mention, if you guys do have a problem like this on your homework, it's perfectly fine for you guys to do, let's say you split it, you're going to have to split the integral like it was done here. But when you split the integral and you evaluate, let's say this side of the integral, and you find that this side is infinite, that it diverges, think about this. If one side is divergent and then you add, even if the other side was convergent, if you add a finite value to something that's infinity, it's still going to be infinite or divergent. So when evaluating these improper integrals, do one at a time. And if you find that it's divergent on the first one, you don't have to evaluate the other one. You can just say it's divergent because already one of them is already divergent. Okay, so let's do 2 examples here, and then I'm going to have you guys try those 2 in the breakout rooms, and then talk to you guys about one homework on your homework tonight. Okay, so on this one, I'm going to have you guys do this each time that you guys see a fraction inside your integral. Okay, fraction should alert you guys, is this improper or not? So if I look at the fraction, I notice that what makes it 0 is x cannot be 0, right? That's where your vertical asymptote occurs. Find where your vertical asymptote is. The easiest way to do that is set the bottom equal to 0. The cube root of x set equal to 0, my problem area is going to be x equals 0. So does that fall within your interval here? The interval from 0 to 1? Well, 0 is one of my limits of integration. So we have that the problem area is this 0 here. That's where my vertical asymptote occurs. So when I replace, now I'm going to replace where the vertical asymptote occurs. So in this case, I'm going to replace that 0 with B. Okay, so instead of infinity, this time it's approaching the vertical asymptote. This is going to be B. The 1 is fine. And as I do that, recognizing that I'm eventually going to have to find the antiderivative of this, I'm going to change that to be x to the negative 1/3 dx. So doing things along the way, so these problems can get intense in that there's a lot of steps along the way. So just kind of anticipate the next step. I would have to find the antiderivative. So let's write it in a way that it would be easy for me to do that. The other thing that you guys want to do is address whether it's coming from the left or right. As you guys are beginning this, some people are better at visualizing this than others, but your interval is 0 to 1. If you're approaching 0, then you're approaching it from the right. Okay, so the interval, if the entire interval is rightwards of 0, then you would say it's approaching from the right. And that's going to be this plus sign that you guys, it's going to be the plus sign that you guys have by the 0. Limit as b approaches 0 from the right. Okay, after that, it's the same step as before. We integrate first. So we're going to integrate first, ignoring the limit. Okay, add 3 over 3, you guys get x to the 2/3, and then times by the reciprocal, so 3/2. Okay, so that's the antiderivative, and then we plug in the 1. So that's going to get me 3/2. And then minus 3/2 b to the 2/3. Okay, limit is direct substitution at this point. If I directly substitute 0 into b, I get 3/2 is my actual integral value. So I would say that it converges and that this function actually gets close enough to the vertical asymptote fast enough such that the area converges to 3/2. So kind of cool to see some of these ideas come into play, especially when we get into the series chapter. All right, so we'll do one more down below here. Every time I look at an integral problem now, I'm gonna think, is it improper? Because in this case, I see that the bottom is x cubed. And once again, my vertical asymptote occurs when where x is equal to 0. So I'll just say x cannot be equal to 0. So therefore, let's set it up as a limit. And b is going to approach your vertical asymptote, in which case it's 0. Same problem here, where you guys have, this is from 0 to 2, and it's approaching it from the right. The entire interval is rightwards of 0. So b to 2, I'm going to rewrite it as x to the negative 3. Okay, if I add 1 here, you guys get x to the negative 2, and then times by the reciprocal of negative 2, which is negative 1/2. I always, and I think I recommended this to someone and they didn't realize that you could do that each time, but I always take the derivative in my head, like times it, subtract 1, do I get back to that? And I do. So that is the proper antiderivative. So this is b, this is 2. Plug everything back in. It's so much switching back and forth, but I like to rewrite it so that x squared is on the bottom. And I'm going to go ahead and plug it in as well. Okay, so this is where your head's gonna spin, some of you guys, as you do some of these problems. Here you guys get something like a finite value. So for sure, this one's fine. When you plug in 0 here, what happens if you guys plug 0 into the bottom? What is the limit as b approaches 0 if you plug 0 in on the bottom here? Go ahead and type it into the chat. What happens here when you guys have a 0 at the bottom? In my mind, I picture 1 over 1 millionth, okay, or some large fraction, or sorry, some small fraction at the bottom. So if we do 1 over that, then what happens is we take the reciprocal, it eventually approaches infinity. So this part of it is infinity, which then means that my answer is that it's divergent. This diverges. So usually the problems will say state the area or state the value at which it converges to, or that it diverges. So in this case, you guys would just say it diverges. All right, you guys. So what I'm going to have you guys do, oh, I had a lot more examples. So let's do one harder one. Let's do example 9 together. Okay, so if you guys take a look at example 9, what you'll notice is that this time it's not 0. That's going to be one thing that I notice people doing. Is like, oh, this is 0, so therefore 0 is the problem. Can you guys type into the chat, what are your vertical asymptotes for example number 9? Okay, very good. X cannot be equal to -1 or 1. Which one is going to cause a problem in this one? Okay, just the 1. We don't have to worry about -1 because -1 is not within the interval from 0 to 3. Yes. So this is hard to spot because this is the one where it's within the interval somewhere. So we're going to split it. So 0 to 1. And we're going to split it at the vertical asymptote. Okay, 1 to 3. So what I like to do is kind of set up my improper integral, make sure I recognize that this is an improper integral. Then over on the right, I'll do what I need to find the antiderivative, just like the very first problem we did. Okay, so let's see. We know that 1 is the problem, so let's let b approach 1. Okay, from 0 to 1, is it going to approach it from the left or from the right? So for this first integral, can you guys type into the chat? Will it be left or right? Okay, good, you guys. So left, if you need to, draw 0 and 1. And then notice that this interval is to the left of your vertical asymptote. So this is left. Okay, and then we have the integral from 0 to b of x over 1 minus x squared. So this is just taking care of the fact that I've set my limit up as an improper integral. If this was a free response, I would take the extra time to do this. This is going to approach it from the right, b to 3 of x over 1 minus x squared dx. So just setting it up so that you have that limit there. So the reader knows, you guys know it's improper. Then from there, over on the right, what I'm going to do is actually integrate x over 1 minus x squared. Let me find the antiderivative of this. Okay, so suggestions, you guys. Think back to first semester. What technique am I going to use here? Okay, excellent. Let u be equal to 1 minus x squared because I know its derivative is something that is linear. So du equals -2x dx. Keep going. If you guys solve for dx, you guys get du over -2x. Okay, the integral of x over u times dx is du over -2x. X's cancel out like it should. We have a -1/2 out front. The antiderivative of 1 over u is ln of u, and u was 1 minus x squared to begin with. So all of that is my antiderivative. So this part, if you guys want to write it out in your notes, is just me finding the antiderivative. Okay, when I get that antiderivative, now I go back to here. And the nice thing is that I can just take this and then move on to back to my limit question. Okay, so over on this side, I have -1/2 ln of 1 minus x squared is the antiderivative I just found. And I'm going to evaluate it from 0 to b, and then just rewrite everything, set everything up as a limit. Okay, and I think I just have to write one of these out for you guys to see. So in theory, you guys, so watch my cursor. In theory, you guys are taking the b, plugging it into here, then subtracting out 0 plugged into here, then plugging the 3 here, plugging the b here. Okay, here's my first step. I do the limit as b approaches 1 to the negative infinity of -1/2 ln of absolute value of 1 minus b squared. And I'm just going to stop there. I know that there's other stuff coming, but watch what happens when I plug in 1. Okay, so if you guys plug in 1, this perhaps is the hardest thing for many students to do. And we tend to, the mistake I see is that this is 0. Okay, that the answer to this is 0. When I plug 1 in, I get 1 minus 1 is 0. ln of 0, and remember it's a limit. The limit as the ln graph approaches 0, okay? Not that it's equal to 0. So think back to your ln graph, you guys. what's your answer? As the ln graph approaches 0, yes, okay, so it's this negative infinity part, okay, it's approaching 0, exactly. So this is negative infinity, and so it doesn't even matter what the rest of the antiderivative looks like. If that part of it is divergent, then the whole thing is divergent. So from there, I can stop and just say that this diverges. Okay, so what an alternate way of doing this problem also is to split these integrals and then maybe just to do one of them and then proceed with one before doing the other one. Some people like to do it simultaneously because you already have the antiderivative, just filling it out. But definitely as you guys get more familiar with these, knowing that you can just stop after one, that's good. And then and make the conclusion that it diverges. But this would be full credit because you guys recognize it's improper, you got the limit going, you do the antiderivative over here, not having to repeat that for each one of these. Okay, so what I'm going to have you